Okay, everybody, so in this section, we're going to add some algebraic expressions which include negative exponents. And what's great about this is that it has a direct connection to what we were doing before when we were adding rational expressions with unlike denominators. So I want to take a look at this first example here, which is a times x to the negative first plus y to the negative first. Now, the first thing that I recognize is that when I have a variable raised to a negative exponent, that's equivalent of having that value in the denominator of a fraction. So what I might do is I might think of a to the x to the negative first all over 1 plus y to the negative first all over 1. And then I say, oh, okay, well, if this is true, then this a to the negative 1 would be the same as a to the positive 1 in the denominator of this fraction. Leaving the a on top, we would get something that looks like this. A over x to the first plus, and the same logic applies over here, that y to the negative first in the numerator becomes y to the positive first in the denominator. So we get something that looks like this. And then we're kind of at the same spot that we were at before with those rational expressions from last week. We can say, okay, well, we've got essentially two fractions here that have different denominators. The LCM, or the least common multiple, of those two would really be the two multiplied together, which would be xm, or excuse me, xy. So then we just have to change them to have xy as the denominator. So a over x, if we multiply top and bottom by y, we get ay over xy. And when we change the 1 over y to the first, we'd have to multiply top and bottom by x. So we'd end up with x over xy. And so now we can just add the numerators as we would with any other fraction set. Ay plus x all over xy. Let's look at one more of these. This one's a little bit more complicated, I guess, in the fact that there's a few more variables. I'm going to zoom in to give myself as much room as I can. First things first, I'm going to write these as fractions. You can skip this step as you get more used to these, I think, but sometimes it can be helpful. And so I'm just going to take them and write them over 1. Then I recognize that anytime I have a variable, a base raised to a negative exponent, that's equivalent to having that same base with the positive exponent in the denominator. So what happens is that I can put the a to the second in the denominator. Here we go. I don't like it. I'm going to erase it. I can put that a to the second in the denominator. I can put the y to the first in the denominator, and then I leave that x in the numerator. Move over to the other expression here, and a stays in the numerator, and the z to the first goes down to the denominator. So now I'm in the same spot that I was in before, now where I have to find the LCM of my denominators in order to add these two together, just like finding a common denominator with fractions, right? So I know that the LCM of these two denominators is going to be a squared yz. I'm dropping those ones because I can. Anything raised to the first is just itself. So what that means is that I need to change each of these so that they have that denominator. Now in the case of x over a squared y, I'm going to just multiply top and bottom by z. So I end up with xz over a squared yz. Then I'm going to have to multiply a over z to the first times a squared y. So I'm going to throw an extra step in here and do a times a squared y. That's the numerator. And then I'm going to do a squared yz for the denominator. One last thing I'm going to do is recognize that a times a to the second is actually a to the third. So we have a to the third y over a squared yz. And I'll add that to my other expression here. And now I have two rational expressions with a common denominator, so I can add the numerators on top. And there you have it. All right, so you got some practice problems out of the book on page 233 for this one. Okay, so changing gears a little bit again, we have problem set 58, which is all about percent word problems. So we're going to go through these in a few different ways we can approach them. Here's the first. Kathy, John, and Susie have only 20 chickens left. If they began with 80 chickens, what percent remains? So I like to think about this as a little bit of a ratio here between the amount that remains of the chickens out of the total. And so we have this information right from the problem, right? The number that remained of the chickens was 20 out of their total of 80, which they started with. So this is a fraction, and we might be able to reduce this and be able to do a quick look at a percent. If we think about the greatest common factor of these, it is 20, so I'm just going to reduce this fraction. And what I get is that actually 20 out of 80 is 1/4. So 1/4, a quick change, is actually 25%. So we got that 25% are the ones that remain out of those 80 chickens. Poor chickens. Baseball cards. Mimi and Jim have 75 baseball cards. They want to give Hal 20% of them. How many cards do they give Hal? Well, if you want to find a percent of a value, as in 20% of 75, a quick way to do this is to take the percent that you have, like your 20%, change it to a decimal by dividing by 100, which would leave you at 2/10, like so, and then multiply that 2/10 times your 75. So essentially you're going to take your 75, multiply times 2/10, like so. And when you do that out, and oh, go on, I remember what it was like to be young. I'll multiply on the side here. Here we go, like a little decimal multiplication. I end up with 15, as in 15 cards. All right, so here's our last example. Bo and Christy hid 600 raisins. Why they did this, I have no idea. This is 60% more than they hid last month. Why are they hiding all these raisins? How many did they hide last month? Well, we can kind of go back to our proportion idea. I like to think about first the percentages that we're comparing. Now this month was up to 160%. Last month was at 100%. And then we had our totals. So with this month, they had 600, and really what we're looking for is last month's, which I think I'm going to represent by the variable r, because, hey, why not? So what I do is I might set up a proportion where I say, okay, well, if 160% goes with 600, maybe I do 600 over 160 is equal to r, which is our missing value for last month, over 100. And now it's a simple process of simplifying these. So what I might do right off the bat is that I might simplify this side. So I might divide 600 and 160 by 10 to get me down to 60 over 16. You could think about this at this point as being a situation where you can undo dividing by 100 by multiplying each side by 100. So I think I'm going to do that right now, multiply each side by 100, remembering that on this side it would be like 100 over 1, like this. On this side, you're going to undo the division, right, by multiplying by 100, leaving the r there. 60 times 600 is 6,000 over 16. And now I just need to do the 6,000 divided by 16. So I'm going to do that. 16 goes into 60 3 times. 3 times 16 is 48. We'll bring down a 0. 16 goes into 120 7 times. 7 times 16 is 112. Leave an 8 here. One more 0 to bring down. And how nice that 16 goes into 80 exactly 5 times. Which means that last month they hid 375 raisins. Why are they hiding raisins? Take a look at the problem set for this one, which is going to be on the next page here, and look at the problems out of the book as well, and those will be your homework.